The first category of nucleophiles we're going to consider when attacking carbonyl compounds will be oxygen nucleophiles. In this case, we have two options, really. We can have our ketone or aldehyde attacked by water, either one here, and we will make what's called a hydrate. And we'll take a look at that reaction. Alternatively, we can have an alcohol attack an aldehyde or ketone. And in this case, we have two different options here. If we're attacking an aldehyde with an alcohol, we get what's called an acetal. And if we do the same thing but with a ketone, we get a ketal. And the mechanism for formation of all of these is essentially identical. The hydrate is half the mechanism that it takes to make the acetal or ketal. Technically speaking, by the way, it's two molecules of the alcohol necessary here for the acetal or ketal. So with this, we can go ahead and take a look at the mechanisms. Typically for these are going to be acid catalyzed. By and large, they can be base catalyzed as well, at least for the hydrate formation. We're going to see what's going to happen here with the hydrate if we take an aldehyde, for example. Doesn't matter if it's an aldehyde or ketone. Again, for all of these, the process is exactly the same, so I'm only going to show it once. What happens is with acidic conditions, for example, and let me move this down just a little bit. Let's look at the acid-catalyzed hydrate formation. And in this, we're going to follow our generic mechanism for forming an acid-catalyzed nucleophilic attack. So, first step will be acid, right? We're going to have our catalyst come in here. We're going to activate our aldehyde. Again, ketone would work just the same. Just have, instead of the H group, it would be something else. Let me just make that a little closer to the lone pair. Once we have that, we have our protonated aldehyde. We have our dear friend, the water, coming in. Remember, that's the conditions that happen here. We pop this open. This is an acid catalyzed process. Again, notice we have no strong bases. So we're not going to use OH minus. Can't use hydroxide as a nucleophile here. It's just going to be plain old water. So we end up with an OH and an OH-H. And then finally, last step will be regenerating our catalyst. We'll go ahead and pluck off that H. By the way, notice we lose H2O here. In this step, we lose H3O+, which is our catalyst. We end up with what's called the hydrate. So this molecule is called a hydrate. This is a hydrate. You might also call this a geminal diol. Geminal meaning they're on the same carbon, diol, two alcohols. So we have two alcohols on our particular carbon here, and we're going to call this a hydrate. For most substances, if we take a look at like the overall mechanism here, for most substances, this is an equilibrium process. We will end up with our hydrate. So in the process, we're using our acid catalyst, and we're going to see that, generally speaking, this reaction heavily favors the reactants here. Products only a little bit. And only, I don't want to say all, because there are a few simple compounds, very, very small ones, can kind of stay in the hydrate a bit longer. In fact, may even prefer the hydrate form. But most carbonyl species prefer to be as the ketone or aldehyde rather than the hydrate. And so we might see this. So suffice it to say, whenever you form a geminal diol in other reactions, they will often very rapidly go in the reverse process. All of these are equilibrium reactions, I should mention, for everything in this section. We're going to see all these are equilibrium, so typically geminal diols will revert back to a carbonyl. So just be aware of that possibility. If we look at acetal or ketal formation, we can consider the mechanism for that as well. This is also an acid-catalyzed process. In fact, acetals and ketals are base kind of immune. They are not affected by bases, which is very useful. So when we're looking at acetals and ketals, instead of using water, we're going to use an alcohol. And because I feel like it, we'll use ethanol in our example. When we take our aldehyde or ketone plus 2 molecules of an alcohol, this is again equilibrium. I should be better at drawing those arrows. What we end up getting is this kind of diether. So we end up with 2 kind of alkoxides on it. And this is called an acetal. If this hydrogen were not here, oh, I guess it is no longer here. If that hydrogen is not there, it's a ketal. So the name is very similar. And the mechanism for acetal versus ketal is exactly identical, so we're not going to show it. So overall, what's happening here is we're going to turn this aldehyde into an acetal. Let's take a look at the mechanism. So just like before, acid-catalyzed process means we're going to have our acid here. And I'm actually going to be better about this. I'm going to draw it as the protonated ethanol, because that would be a better choice. Because typically we'll use sulfuric acid, which has a little bit of water, but we'll go ahead and have ethanol be our acid source, the protonated ethanol. All right, here we go. We're going to go ahead and attack. Generally, by the way, sulfuric acid or toluene sulfonic acid are commonly used acids for this process. So we lose an ethanol from this, and we will get our protonated species. Ta-da! And just like before, we're going to get this attacked by one of our ethanol molecules. So very much the same as the hydrate formation. Pops it open. And again, all of these are equilibrium, but I'm lazy and I'm drawing them 2 double or single arrows, but they're all equilibrium steps. So this is a 100% reversible reaction. So we have OH here. We have our protonated form here. Another ethanol molecule can come around. And we're going to regenerate our catalyst. So we're going to go ahead and deprotonate. We lose our H2O ethanol thing, so we have our acid back. And now we have this kind of halfway in between molecule. This one has a special name. This is called a hemiacetal. And there's, of course, the equivalent hemiketal form as well, which would have, oh, speaking of which, I need that H there. Oh, we've somehow turned into a ketone throughout this whole process. Oh, no. So a hemiacetal has a hydroxy as well as an ethox or an alkoxy. So it's got both an ether and an alcohol on the same carbon. We call that a hemiacetal. Hemiacetals are typically unstable. So this will be kind of the highest energy point in our entire process. Unstable if linear. We'll see later on at the very end of the course when we talk about carbohydrates that cyclic hemiacetals are stable. But if they are non-cyclic, so if they're linear molecules, they are unstable. So that is our hemiacetal. The next step in this process is we are going to have our protonated ethanol come in here again, and we're going to have our hydroxy attack it, grab that proton, producing another molecule of ethanol. So it's really essentially the same set of steps as the first, we just do it again. So first step, we protonated our aldehyde, then it got attacked, then it got deprotonated, and now we're doing exactly the same thing. So the OH will attack, we lose another molecule of ethanol as a byproduct. We have now our leaving group set up, because now what's going to happen is we're going to have our ethanol molecule come in and attack, and it's going to kick out that leaving group. So here we go. Comes in, kicks out the leaving group, which is our water. So we have lost water in this step. We have following, and as before, it's protonated. So as we know, the last step in an acid-catalyzed process is deprotonation, and that is exactly what's going to happen next. So we'll have another molecule of ethanol come along and deprotonate it, leading us to our acetal. Acetals and ketals, we have turned into a ketal because I keep forgetting that H is there. Acetals, I'm going to move this over, are stable. You can isolate them, and in fact, this is an excellent way of protecting a carbonyl compound. So we can use an alcohol in acid conditions to protect a carbonyl. This is going to be base kind of immune. Try and put this with bases, nothing's going to happen. We can remove it with acidic conditions as before. So we can protect our carbonyl, do some other reaction, and then deprotect it later. So their most kind of useful functionality is as a protecting group. So often, their best use is as a protecting group. So because aldehydes and ketones are very electrophilic, they're going to get attacked by things. We can protect them using acetals or ketals. Note that an aldehyde gets preferentially attacked, preferentially protected with stoichiometric alcohol. So if you have a ketone as well as an aldehyde, for example, and you put this with exactly 2 moles of your ethanol, or whatever it may be. Let's use methanol this time, because why not? Put this with some acid and heat. We will preferentially, because the aldehyde is more reactive, we will have our ketone here, which now that our aldehyde is protected, we can go ahead and react our ketone. We can do whatever we need to do with our ketone and have that undergo some other reaction. Remember, again, more H plus and water and heat will take that away, giving us back our aldehyde. So we need water. We need alcohol and acid to get the acetal on. We need water and acid to take it off. So we hydrolyze it. And it's also very common to use diols to protect. And when you do this, when you use a diol, for example, let's use that same molecule. You only need one molecule of it. So you can use ethylene glycol, for example. It's got 2 alcohols on there. Put this with some heat. You'll end up protecting that aldehyde in kind of this cyclic way. And this is even better for protecting if you have 2 different carbonyl compounds, because you're only including one equivalent here of your alcohol. So it's a little bit easier because they're on the same molecule, so it's easier for it to happen. And just like before, you can treat this with water, acid, and heat, and you will deprotect your aldehyde. If you don't have an aldehyde, they'll protect your ketone instead. You'll make a ketal instead. If you put 2 equivalents, you'll protect both of them. So it just so happens that aldehydes will preferentially, because they're more reactive, will get protected first, which gives us extraordinarily useful synthesis pathways in which we can now react our ketone but leaving the aldehyde aside. If we only want to react the aldehyde, by the way, we don't need to protect anything because the aldehyde is always more electrophilic. So we can have our aldehyde get attacked preferentially if we put one equivalent of whatever nucleophile. It'll always go to the aldehyde. But if you want the ketone to react and not the aldehyde, you've got to protect it. And this is a great way to do it. This last one here with the protecting group that's cyclic is very common. So you'll see that. This is an acetal as well, just like before. All right, so that covers acetal and ketal formation. Hydrolysis of this is exactly the opposite. So everything happens in reverse. You start with your acetal, you'll protonate it, get it protonated. You will then kick it out by having water attack now, kick out your protonated alcohol, and just keep going in reverse. So the mechanism is the same in reverse, but we'll take a look at it anyway in our next video.